Welcome everyone. I would never imagined when I filed this talk for DevOps that I would speak for a full room, or almost a full room. So thank you all for joining this session where I'll give you an alternative for storing your data instead of using an external system. Most of the time I'm going to say database because databases are used most of the time. But it is a general thing. So every time I say just database, think about external storage, external to your Java program. Because we have our Java program with statements and objects, and there are data in it. They even form normally a nice object graph. So you have all the references between your different parts of your data model. But those data, they need to come from somewhere. And most of the time, we read them from just a database externally, tables, fields, records, etc. And there are two main issues with that. First of all, it is external. So that means if you're going to read those data, then there is the latency. Before you get them back, that can take some hundreds of milliseconds, and depending even on the system, the network topology, or even in the worst case, which you normally should never do when your program is not running in the same data center as your data storage, for instance. But not only the time to retrieve them is an issue, or can be an issue, and that's a bit simplistic, but database, it's most of the time just numbers, text fields, and dates. And with Java, we have our rich object model, so we need to do a conversion. We need to convert those individual pieces of data. We need to assemble them, probably stored in different tables, in different records. We need to assemble them all again back to the objects, because we have a nice program that works in an object-oriented way with an entire hierarchy and an object graph. So those two main things can hurt you a lot in a program. Was it wrong of Java to choose to use a database? Well, no, because databases were there at the beginning when Java was invented and was used for enterprise applications. So it was normal that people start using the database, existing databases, existing data storages to retrieve the data, but maybe in a lot of cases there is a better alternative. For those who does not know me, I'm Rudy De Busscher. I'm working as developer advocate for MicroStream, but I'm also involved in MicroProfile and the Jakarta specification, so you can also find information if you follow me around those topics. And yeah, data is everywhere. I don't think that there is a real enterprise application, Java enterprise or whatever kind of application, that's not dealing with data. The data is, as they say, also the gold mine of your company. Data is the most important thing in most cases. That can be from your web shop where you have the products, the shopping basket, can be in a manufacturing environment with the orders, stocks, the planning, customers, data from healthcare, IoT, automotive data, whatever. Maybe there are a few applications that look for data elsewhere from external sources, process that, manipulate that, and return it. But let's say all applications deal with data. So that's very important. And that's probably also the reason why there is some pages on the internet which try to list every data storage solution that there exists in the world. And there are more than 350 different types of solutions, each focusing on a single feature, single functionality. But as we said, data comes externally, so you have the latency, you have to convert it, and even if it's not a real, if it's not a database but a NoSQL solution, like a key value store or a graph database, a in-memory data grid, whatever, you always need that conversion, that object relational mapping thing. And that's described there with that rather thick red block, because there are a lot of functionality in there, and you find there amazing pieces of technology, those object relational mappings that tries to map your Java object structure to the external representation and tries to hide all that functionality, all that complexity from the developer. But since it can be complex, you have all kinds of complicated, for instance, in Hibernate, the hierarchical mappings, you have all kinds of conversions. It is also generic, it must be generic. So it's a lot of things that you need to learn as a developer. There are also experts probably needed if you are running it in production to find out what it is really doing, if it's the ideal, or how you can tune it so that it is ideal for your situation. And yeah, that object relational mapping hides it, but then what we do in those, or what the idea is in those applications, is that we just want to store it. We don't care anymore. Is it a database? Is it a NoSQL solution or whatever? So basically, we are just dumping the data there just to be retrieved. So it becomes a serialization. But as a serialization, there are much better solutions. Of course, there are exceptions. For instance, if you are using data in a graph database, for instance, you are using that path traversal algorithms, etc., then you are making use of that external system. But most of the time, it is just store the data for when I need it and get it back when a user requests for it. But you all know that, but just I want to make the comparison what you probably do most of the time with something you can do with another solution which is much easier. For instance, if you have queries written in Hibernate query language, API query language, okay, they need to be parsed. The parsing, the tree is then stored, so that takes up memory again. And since we are in those queries actually querying objects and not data, the optimization that I did is they added a cache, which is rather funny because if, for instance, in JPA, in this specification itself, there is explicitly a mentioning of two caches, the first level and the second level cache. So if you put already in a specification that, oh, you will need those caches because otherwise it will not be performant, then you know what you will end up. So the cache needs to be checked. If the objects are not there, then of course they need to be retrieved. That means that there is a conversion required to JDBC calls, and then we all know that n+1 select problem that we can have. So tuning needs to be done there so that we don't go 1,000 times to the database to get our initial data. I was once with a project. They asked me, why is this startup so slow? And by just tuning, by just setting on the statistics, loading their homepage, their initial page for the user, issued 3,200 queries. Because they misconfigured their laziness, eager fetching, and all those kind of things. But if you have tuned your query, then you can have also issues on the database. The database, you have statistics on the database, on indexes, and you use a simple query where your where clause is on a field which is indexed. So what can go wrong? Well, what if the database statistics are not updated and the database thinks, oh, there are only 10 records in this table, so let's do a full table scan. but actually there are 1 million records. That's of course the area of our DBAs, but it all comes together in this simple get me the data that I need for this request. As I mentioned, you have to convert it to objects, then probably you need to update the cache because you don't want to do that next time, a second later when another user queries the same data, etc. So a lot is going on just by the requirement of, hey, I need my data for my process. If you want to learn more about those mismatches and those issues, look at the internet, search for the words impedance mismatch. There are a whole type of mismatches, and they all play a role in why it sometimes can be so frustrating to get data from your external storage. But what if we just are thinking completely out of the box and trying something completely new? I mentioned already that our program is using Java objects, Java instances in the heap, because eventually they need to be there. What if we say that the data itself in the heap is our database, the primary data source? So not that we are retrieving it from elsewhere and use it, because then that external system is the primary source. What if we say that our Java objects in memory in the heap are the primary data source? There are a few issues, I come to that. But if you say that, then of course querying is easy. You don't even need any query language anymore. Well, maybe you can say you can use the stream APIs as query language. It's also fast because it is in memory. It's easy for the developer because he only needs to use Java constructs, which he probably knows or he should know. He does not need to learn those frameworks, and it's also fast at runtime because, as I said, data is in memory. Of course, if your process stops, dies, whatever, your data would die with the process, so that's an issue. So that's where MicroStream comes in. And they created a new serialization engine so that you can store your Java instances in a binary format to an external storage location. It's something new. It's not the Java serialization one. For one reason is that, for instance, the standard Java one requires that implements serializable. And the idea is that every object should be able to be part of your database, so every object should be able to be stored externally. There is also, of course, functionality to evolve, migrate your data, so it is a very advanced serialization engine. And then instead of all those steps, as we have seen, querying becomes a simple thing like just select within the JVM, like we do every day, every minute of our development life. And instead of retrieving the data from that primary external source, we are storing the binary representation of our objects that we say this is our database. We store it externally because, as said, we need to be able to have the data again when we start up the process. That binary data that can be just on disk in a file. It can also be in a database, but then not as fields and tables, etc., but just as a binary large object. You can do it in a No-SQL solution. You can do it in the event streaming systems like Kafka, whatever. You can do whatever you need for distributing the data, for instance, but the idea is that you store just a binary externally so that the process can access it again later if it needs to be. And then that thick red layer becomes there a very small blue layer called MicroStream, which is included in your application. which makes sure that the data is retrieved at the beginning so that you have it in memory and that you can also access to store any change, because just as with a database, if you change something, if you change your data, you need to say, keep me this change for later reference. And it's a thin layer now because, yeah, most of the time developers maybe are using like 5 classes and 20 methods. That's all what they need. And it's also small in size, so it is very easy to learn and efficient at runtime. So let's have a look at a few demos so that you can get a better idea of how that might work for your application. The entire code can be included by one dependency. It's available on Maven Central. It has a few transitive dependencies, but it was explicitly by design that there were no external like Google Guave of Apache Commons there, so that you did not have any issues when you want to combine it with your own dependencies. The only thing that we have is here the SLF4J API for logging. And let's start with the hello world, of course. What else? There are two important things when you get started with it, and they are reflected in this simple statement. Two things are important. One is that you need to, I'm trying to get it a bit bigger, which is not working, my shortcut key for some reason. You need two things. One is that you need to indicate, well, this is my starting object of my object graph. You only need to specify one instance which is part of your object. Most of the time we call it root. It is most of the time a tree, so you take the top level or the bottom level. That's how you describe it. And the rest is discovered through following all the references. And the second thing is that you need to identify where it is stored. In this case, I'm saying it is stored in a directory called data. That root here is just a pojo, no interfaces, no extensions, no annotations, pure Java. It can be anything. I should maybe have used here a date time instead of a string, because it can handle any kind of object out of the box, and a product here, which again is just a pojo. By default, I do a new one, so it will be empty. There is no data yet, so there is no database, no directory. So when I run this, I print out the root, which is then of course empty. Timestamp is null, product is null. No surprise there, but it works already. Because in the next step, for instance, we can set the timestamp that it's the current date time. The product is null. That was a little of safety, but if it's null with it, then I add a few products there. I add 4 products and I store the root. So I store what is changed. I say to the system, keep me this for later reference. Showing the contents again, and now there is some magic happening. I instantiate here an empty class, but through this start, he sees that there are some data. Here are the data, more on that in a moment. So he populates the entire object tree with the serialized data there. So behind the scenes, there is some reference manipulation, pointer manipulation, and we see that the time was 10:54. Keep that in mind because that's one of the things that I want to show you, and 4 products. Data is here in a binary file, So yeah, it's binary. And actually that contains only some references and data. So it contains identification of what that piece of data is, what follows next. And there is then what we call a type dictionary, says then, okay, that product that we have, that is this unique ID 1,069,000, which consists of a string, a product type, and a long. And it was these property names. So that's used for that data evolution schema thing, what I mentioned. But if you want to learn more, I can tell you after the presentation about it. So we have products now. So we're going to add one. And the golden rule of MicroStream is store what is changed, which can be a bit different than in a database system. So what is changed here? I have this list here. I add a new item to that list. So what is actually changed is the entire list, because I have added a new item. System is intelligent enough to find out that there is not actually 5 new things that he needs to store, but only 1, and he stores only that 5th product that I'm going to add here. I also changed my timestamp here, but actually that's outside of what I'm going to change, which I'm going to store, sorry. It is changed, but I'm not going to store it, so actually I lose that. So same as with the database, if you don't say that it needs to be stored, then, well, if your process stops, it is gone. Or when your object is garbage collected, is gone. So that's why I said, keep in mind 1054, run it, he adds the 5th product there. If I'm going to show it, the content of the database, it is there, it was pizza, but the timestamp is still the same. So it's not updated to 1057 or something, which is now the current time. Same thing, an example of the query language that you can use. For instance, I want to get that last added product because, yeah, pizza is maybe for entertainment reasons, but actually it is more food than entertainment, so I want to change the product type. So I can find that item with the Stream API. I can change this enum value, what is changed, this one, this object is changed, so store that one. Again, for comparison, I changed the date, but that will still be the same. I can run this update. He only stores actually that new enum value, so it is only storing the changed bits and pieces, not everything. And then based on when your storage manager startup like this one, based on all the information, bits and pieces, a bit like Git, he assembles the actual last value that needs to be in the memory. Config, as I said here, 2 important things, a bit more, because most of the time in projects you are not using this one, because that's a bit too limited. If you're doing it programmatically, you can define that information from, like, instance, for example, the directory and channel count. More on that in what that means in a minute. Through a builder pattern, so you can have a lot of things. You can define the data file, maximum size, naming conventions, because you saw it, it was a .dat file, DAT file, you can change that extension, etc. So you can customize a lot of things. You can all do that through that builder, and then you call what we name it as a foundation. So the basis, we have all the basis information there. You can even, which is large, because everything within MicroStream is an interface, so you can replace it with your own version if you like. You can adapt the version what we provide. You have everything. You can add additional things like specific handlers, specialized handlers for the new JDK 17 immutable collections, for example. You specify the root, and then you create that storage manager, and don't forget to start it, because sometimes I forget to start it and I'm saying, why I don't see any data? Because yeah, it's not started. Instead of using this, okay, you can of course externalize these values through properties, whatever system you're running, Spring Boot, Quarkus, Jakarta, whatever, you can always read those values from somewhere and use them. Or you can directly use a property files or XML file. Those are the two by default. Again, it's an interface, you can implement it so that you can change it on the fly. Even, for instance, in test, you have something stored on disk, but in production, you are storing it maybe in a database, or as we will see in a moment, you can store it also in cloud storage locations like Amazon S3 or others. By just having the correct values here, you can specify, for instance, that there is Postgres used, but actually, most importantly, you need to specify a provider here that implements this class, which will be called by MicroStream, calls your code to get an actual connection to the database where it can store your serialized data. These URL, username, and passwords, these are the properties that you have specified here. So you can even call them XYZ, but URL, username, password sounds a bit better. I mentioned S3. So if you get an S3 client instance from the Amazon SDK, you can use the blob store file system. We have an abstraction called the AFS, abstract file system. Show it to you in a moment what it means. Then it can store something as a blob somewhere where that's then defined what you specify, and we specify here the S3 connector with that client. And you specify the S3 bucket name where data needs to end up. Expert level, as I said, everything is an interface. So the simple thing of defining a disk that's backed by the non-blocking I/O file system in Java. You see you have providers, builders everywhere. So that this is the expert level of configuration where you can define every little piece what needs to be executed. So we have done config. We have seen that we can store data, read data. The next question that you have in mind, what if I have a lot of data? Can I have something like a few hundred gigabytes of data set and run it in 4 gigabyte of Java heap, for instance? Yes, that's possible. But not all your data is accessible all the time at any given moment, of course. The idea is, especially if you have binary data, large objects, historic data, for instance, you have a table with all your purchases from the last 10 years. You don't need that in memory, those 10 years. You only need the last month or something, and occasionally you need to address those old data. So that means that those old data, to say it a bit inelegant, the old data can be stay on that external storage. They don't need to be loaded into memory when your storage manager starts. And you can define that by putting a lazy object there in your object graph. And lazy means that you have a proxy. So instead of loading the actual list of trip details data as I have here, you just instantiate a simple class. It's around 1000 bytes, which is capable of retrieving the data when you access them, but of course they are not in memory at that given point when the storage manager starts. Lazy has a get method so that you get the actual data. So if it's not loaded, it loads it. Peek doesn't bother of loading it if it's not there. You can clear it so that you can free up the memory. because this lazy concept is based on the weak references of Java. So every time the garbage collection runs and sees from, oh, I am a bit short in memory, I need some space, then the garbage collector is free to throw it out, which is not a problem, because when you access it with get, you can load it again. The example here is about 3 million of data. That trip details here, where here is it? Here is it the trip details. So quite a lot of fields. So I try to be a bit realistic. It contains 3 million data of a taxi driving company for 1 month. So all the trips they did with when they picked up people, the number of people, etc. So all the data. So when I start my storage manager, it does not load any of those 3 million data. It creates only, let's go back to here because it was really quick in the moment. So it's a map by day, organized by day. So the key one contains all the car drives that I did on the first day of the month, to the second, etc. So when I load the details, then it actually goes to load it from disk and I get the information. So let's see a bit of timings. So let's start it up. And at the end, so I load day 1 here at the beginning, but also at the end. And in between, I also show the free memory, but that's not always conclusive because you can have a garbage collector which can free up some memory, and it is here the case again. It's always funny if you do that demo. So I'm loading the data for day 1. I'm loading about 100,000 records in 1 second. So there are 3 million on disk, but he does the querying itself, saying I'm only loading the data from day 1. So if looks what it needs to load, and you see actually there was more free memory after I have started that process, because yeah, that 1 second here includes also a garbage collection run. So you see that's not that bad. I load 3 more days, and then you see, as it should be, each day is about 100 megabytes, so it's about right that it then goes down with 300. And the last thing here is I'll access that day 1 data again, but it is of course instantly because it was already in memory. That was not thrown out. I had more than enough memory. So actually, it was, 10 minutes of demo, and I showed the entire MicroStream. There is nothing much more than that. There are a few, of course, advanced topics, etc., but you have a few things around configuration, that store method, and that lazy reference, and for the rest it is pure Java. So if you know Streams API, you can work with your data, of course. So you don't need that domain-specific language for queries, views, inheritance, converters. Forget all about that. It's much easier. Especially if you just want to dump your data somewhere and read it back again when you need it, which is, I guess, in most cases. Mentioned abstract file system. So in order to support disk, S3, Amazon S3, etc., so we have an interface. So the storage manager only works with that abstract file system, and implementation then knows where to store it and how to read it, etc. We support, as mentioned, databases, blob fields, and disk. The serializer runs in a channel, and a channel is a thread which is performing serialization back and forth to the binary, also performing the data evolution, which I don't have time to show, but you have 1 thread, 1 channel, or you can have multiple, so that you can process more data if you have more data or high burst, high peaks in changed data. For instance, then if you want to speed it up, then you can have more channels. Mentioned lazy for that binary data like documents, images. For historic data and automatically handles, there are a few additional things that you need to know around lazy and how we manage it and how the memory is managed with the weak references, but the basis I showed you in the demo. All that is available in the open source version, and it basically works with you have a single JVM which can store and retrieve the data, which means clustering is a bit of a challenge. And we provided a class, it's called ComChannel, which is based on top of the asynchronous socket channel of the JVM, so that you can distribute data, distribute your object graph in multiple versions, in multiple instances, if you like to do it, if you would like to create clustering yourself. But then you have to do it manually. An example is that you create a server process which handles actually your object graph and stores it to, for instance, Amazon S3, and then your applications, which can be running in 5 instances, communicate then with that server through that COM channel to update the data, to retrieve the data, etc. There is a reference to that GitHub account where where you can find the following example, so that to showcase how you can use it. Here it's a video because you see it's a bit of screens, and I didn't want to do this live because the demo gods are not always happy on conferences. But on the bottom left, you have the server, which is just a plain jar file, which works with those COM channels. On the top, you have 2 Payara micro instances of your applications. So the first one on the left is running on port 8080, the right one on port 8181. So 2 versions of our applications, 2 exact same versions of application. So if we curl our first instance for the list of products, it's not there, so it contacts the server and it gets the list of the products, and it is also cached in that instance, of course. You can do for the same for the second instance, port 8181, and it retrieves the data and it shows it. What you can program then is that when you post to the second instance, for instance, a change, a new product, that change is also sent to the server, and there then broadcasted to all the other instances, so that when you access then the first instance, that one also has it automatically, immediately, so without the need to contact the server again, always over and over again. So you can have an initial pull of the data, of all the fixed data, think about non-lazy data, into your instance, and then the server can push any change to all the other instances if there is an update. And that's the manual thing, but it is the same idea that we have implemented in the enterprise version, but of course with a few other systems. Namely, there we are using Kafka as a storage and the organizer, so that and that all the data is stored and available on all your instances. So you just interact with the storage manager. This is running within a Docker environment on AWS for the moment. More systems will be provided in the future. And so that means that you have just to develop your application as usual with the storage manager, and you deploy it through that enterprise product. And this running in that environment in a clustered way with scaling and all the things that you can imagine, of course. I mentioned also a few times it is faster, so show me the numbers. How fast is it? You can find the example there again in that GitHub repo, how you can run it yourself and reproduce everything, what I'm showing here as a conclusion. First one is the write performance. So it was already prepared there with that trip data details with the 2.8 millions of records, but how long did it take to read a CSV file with those records and store it with MicroStream, store it with plain JDBC, and store it with Hibernate. Loading from the CSV just in memory took 9 seconds, and MicroStream needed an additional 40 seconds to store it again then on disk. JDBC and Hibernate took much longer, 94 and 116 seconds, so twice, up to 3 times longer. Due to the conversion, due to the latency, and in this case with inserts, the database checks every time, is that primary key value unique that you provided? So he has to do it many times. So the examples are using batching, but even then the database, the last record, you have to check, oh, is this unique in those 2.8 million records? So that takes time. But it can be even more performant if you're going to read, because there you actually only use the JVM. You're not going external anymore. This was a simple query, meaning you have the customer table in that example where I do just a select from the table for the first 100 records and then the next 100, so a paginated way of reading the data. And yes, the first time MicroStream, when it starts up, so I included that one in the green, the first time it starts up, it needs to access the data and load it into memory. That takes time, but the query itself took only, so the 3 queries in total took only 20 milliseconds. So JDBC, the connection there was 200 milliseconds to database. It took longer to execute the query. In total, as you see, the bar is shorter the first time, yes, but if you then go for the second queries, then you see MicroStream 20 milliseconds, JDBC and Hibernate 130, 140, so 7 times slower. And it can be even more. A complex query where we have a lot of tables joined because we have a customer address which has the address itself, so the name of the street, but the city, the country, etc. So we need to join a lot of data, a lot of complex joining required. And to make it a bit more fair, it was only historic data, so the first time MicroStream also needed to load all those lazy loaded data, but even then, in that case, it was much faster. Because the query with JDBC and Hibernate took 2.5 to 3.3 seconds in total to query those, to execute those 9 queries in total. Which means one individual query is about 300 milliseconds, which is, okay, it's doable, but if you can get your data from those 9 queries in 5 milliseconds, then 3 seconds is a long, long time. So we have the statements, MicroStream is lightning fast, and I guess we can prove it with some numbers. Actually, it is as fast as the JVM, and so if the JVM goes faster, then we are going faster. What are typical use cases? We see 3 of them. First of all, there is today the tendency of having a database for each microservice or each domain-driven, each domain, which means that, again, the latency can hit you because you need to access a lot of microservices before you have the data, which means data are cached locally. If that is done with MicroStream, then you have the advantage that when your cache starts up, it's already loaded, pre-warmed, so you have all the data already, and then An event system can be used to update those data as they are updated in the respectively different microservices. Serverless, load the data what is needed for a request. So your process starts up, make their excessive use of lazy, I would say. So don't load a lot of data, but when your request needs a certain segment of your data, you can lazy load it and use cloud storage like S3, etc. They're again much faster than having a database, because then you have also the cost of having the database running, because that cannot be started up and down, going up and down as with the lambdas. And every time making that connection to the database and getting the data can be also very time consuming. And the third use case that we see is for Android development, mobile development, where you replace it see as a replacement of SQLite for an offline first strategy, where instead of using SQLite to store it locally, you use then MicroStream to store it locally and sync it up when you have connection. It's pure Java, so it can be used within any JVM language, so also Kotlin, Scala, Groovy, and Android, as I mentioned. Can run everywhere where Java is running. Version 7 currently requires 1.8 as JDK version, but also works on 11 and 17, etc. But on-premise, in container, wherever you like it. Storages, as I said, databases, No-SQL, we can store, for instance, or use Kafka as an example, or Amazon S3, or the Azure Blob storage. It's already integrated within Helidon, so it is with Helidon SE and MP, you can have a dependency to use it integrated. So it's not the classic MicroStream dependency, but you are using the Oracle dependencies. But there are also integrations that we have created for the Jakarta runtime Spring Boot and also Quarkus, but there we need JDK 11, so that one is not released yet. But if you build it yourself, you can also use it already. More info, the website, microstream.one, we have the GitHub repo there. And if you have any questions, you can find me here, or you can go to Stack Overflow and get your answer there. Thank you for your attention. I would say enjoy the conference, but it is almost over, so I hope you enjoyed it, and I hope to see you once again sometime. Thank you.